Intervals for normal distribution. In the preceding module, we described how we derive this bell shape for a variable that is normally distributed. So first we look at its distribution, which represents all its possible values, and then we look and see what the frequency is of each of those possible values. So once again, just a quick recap, the average occurs the most often times, and that's probably the most distinctive observation for normal distribution. And then of course, as you deviate further from the average, those outcomes are less likely to occur, and therefore when you connect these dots, you get that bell shape. So what have we done a little bit differently here? Well, rather than looking at the values of all the possible outcomes, what we're doing here is we're expressing the outcomes in terms of how far they deviate from the mean in terms of standard deviation. That is the only difference. I'll say it again because it's very important. So rather than looking at the actual values of this random variable, what we're doing is we're restating the horizontal axes in terms of how far the outcomes deviate from the mean in terms of standard deviation. And these are important rules of thumb to know, because later on when we look at these probability tables or distribution tables, the only way we can find out probabilities up to a certain point is if we indicate how far we deviated from the mean in terms of standard deviation. So what are these rules of thumb? There's really only 4 that we need to know. So if we were to deviate 1 standard deviation on either side of the mean, that would cover 68% of all possible values. So what that would mean is 68% of all possible values would fall within this range. Now mind you, if we start from from the left tail to the right tail, that would represent 100% of all observations. But in this case, if you just deviate plus or minus 1 standard deviation, that would just represent 68% of all observations. So if that is true, 68% falls within this range, and we know the distribution is symmetric, we can then work backwards and calculate what the probability is of each tail. So that's the other thing we have to become familiar with, is the terminology. So this would be the body, and these would be the tails. So if the body makes up 68% of the 100, that would leave 32% split between 2 tails. Therefore, each tail would have a probability of 16%. So now let's look at the other range. Again, always starting from the mean. Always start from the mean. So if we go 1.65 standard deviations to the right and 1.65 standard deviations to the right, to the left, between this range, we can expect to see 90% of all observations. Now, if the body makes up 90, that means you have 10 left for the 2 tails. Therefore, each tail would have a probability of 5%. The next rule of thumb is 1.96. So again, starting from the mean, if you go 1.96 standard deviations to the right and 1.96 standard deviations to the left, within that range, ladies and gentlemen, you can expect to see 95% of all possible observations. But that would leave 5% for each tail. Therefore, each tail would have a probability of 2.5%. And the last rule of thumb that we need to know is the following. So again, starting from the mean, if we go 2.57 standard deviations to the right and 2.57 standard deviations to the left, within that range, we can expect to see 99% of all observations. So if that's the case, that leaves 1% split between 2 tails. Therefore, each tail would have a probability of 0.5%. And again, ladies and gentlemen, these are very important rules of thumb. So important that I'm going to restate what we just discussed in table format. So again, we're looking at deviations from the mean, so plus or minus 1. So the number of observations within that range is 68. That means the probability of each single tail is 16. 1.65 gives you a 90% confidence range. That leaves 5% for each tail. And then we have 1.96. That gives you 95% range around the middle, leaving you 2.5% for each tail. And finally, if you deviate plus or minus 2.57 standard deviations from the mean, that gives you a range of 99%, and thus leaving 0.5% for each single tail. Now, for any other deviation from the mean, in other words, if you're looking at a standard deviation that's different from these 4 rules of thumb, then we would have to use the standard normal distribution table. And we will show you that in a later instance. So let's do an example. Suppose that the stock has an expected return of 12% and a standard deviation of 9%. And let's assume that the stock returns are normally distributed. In part 1, we're asked to calculate the probability that the return on the stock will fall below minus 2.805. Now the thing is, for us to determine the probabilities, so for us to determine these probabilities, we have to identify how far we are from the mean in units of standard deviation. But if you look at the question, that's not the way it's expressed. It's just telling us what's the probability that the return will be less than minus 2.805. So what I've done here is, so I'm still going to use our framework, our normal distribution framework, but now I'm going to have 2 horizontal axes. One plots the actual number, and the other one plots the deviation in terms of standardized values. In other words, what I want to know is this minus 2.805, how far does this deviate from the mean in units of standard deviation? So let's set this up. So here's the mean, 12%. So I'm plotting the actual values first. And the critical return is minus 2.805. And then we have to ask whether the author wants to know the probability of the body or the tail. And that's where we have to read the question carefully. It says, what's the probability that the return will be? Less than. So the author wants to know the probability of the tail. Now, as I said before, for us to determine the probability under this curve, we have to indicate how far we are from the mean in units of standard deviation. So there's your calculation. How far is this number from the mean? So that's the numerator tells us what the deviation is between the observation and the mean, but that's using actual values. If you want it in units of standard deviation, we have to divide it by the standard deviation. So the value of the standard deviation is 9. So therefore, the way to read this is as follows. This critical return is 1.65 standard deviations to the left of the mean. Now this I can use in order to calculate probability, because if you go to our table, the one that we had done, here it is. If you are 1.65 standard deviations away from the mean, or here, let me do it this way. Visual is better. Let's use our visual framework. If you are 1.65 standard deviations away from the mean, now notice, ladies and gentlemen, it doesn't matter if I'm looking at negative 1.65 or positive 1.65 because the distribution is symmetric. So the area under this tail is the exact same as the area under that tail. And what is the area of that tail? 5%. And that's how it works. So let's go back to our question. So the probability that the return will be less than minus 2.805% is 5%. So now we can work backwards and say, okay, well then what's the, so if this is 5%, if that's 5%, what's the probability that the return will be greater than minus 2.805? Well, we know that the area under the curve represents all observations. In other words, the area under the curve is 100%. So if this tail is 5, then the body would be 95%. And that's exactly what we got. So now let's go to part 2. In part 2, they want to know what's the probability that the return will fall between this range, i.e. minus 2.805 and 12%. So notice my approach is always the same. First, I identify the framework that I need in order to solve this question. And clearly, I'm going to use the normal distribution framework. So there it is. So the first thing I want to do is I want to plot the actual values. So I know this is the mean. I know that's the mean. And the critical point here is minus 2.805%. Done. What's the next thing? What area under the curve are they interested in? Well, they want to know in between these two values. So it's the red shaded area. They want to know the area of the red shaded area. And remember, area under the curve is really the probability. So how do I find the area under the curve? Now remember, we know that the total area under the curve is 100%. But what else do we know? Since it's symmetric, each side represents 50%. And that's exactly the calculation I'm doing here. So if you're looking at everything below the mean, so if you're looking at from here all the way down there, that represents 50% because you're looking at half the distribution. And from the previous part, we determined that the tail area here is 5%. So we just got to find in the plug, right? Let me run that by you again. The probability that we'll see anything less than 12 is 50%. The probability that we'll see anything less than minus 2.805 is 5%. So then what must be the probability of that gap in between? Must be 45%. So therefore the probability that the return will fall between minus 2.805 and 12% would be 45%. Now in part 3, they want to know what the probability is that the return will be greater than 25%. So same steps, ladies and gentlemen. We take out the bell shape, which is the normal distribution. And first we plot the actual values, and that's the data that's given in the question. So here's the mean, that's 12%. And the critical value in this case is 25%. Good. Now we have to determine the area under the curve that the author is interested in. So they're interested in the probability that the return will exceed 25%, so they want this tail area. Okay, now remember how this works. For us to calculate the area under the curve, i.e. the probability, we need to determine how far this critical point is away from the mean in units of standard deviation. So how do we do that? Well, here it is. So how far is 25 away from 12? That's the numerator. And then we divide it by the value of the standard deviation, which is 9%. So therefore, the way to interpret this is the following. 25% is 1.44 standard deviations away from the mean. Why is it important for us to look at it that way? Because now that I have the standardized units, in other words, deviation in terms of standard deviation, this is the number that I can look at in the normal distribution table in order to get the area under the curve. So that's exactly what we're going to do. So I'm going to take you to the table, and we're going to see the critical value of 1.44 standard deviations away from the mean. So here we are. This is your cumulative probability distribution for standard normal distribution. And the way to read this is as follows. So remember we said we're 1.44 standard deviations away from the mean. So first we identify 1.40, and then you can think of these rows as fine-tune adjustments. So you can see it's sort of like the second decimal adjustment, if you will. So here's 1.40, and then this over here would be that 0.04. So combined, so if you triangulate, this here would tell you what the area under the curve is up to 1.44 standard deviations away from the mean. And the other way that this table accumulates area is it starts from the leftmost part, and it tells you what the cumulative area is up to the critical point. So you could see it's 0.9251. So now let's go back and look at our question. And here we are. So starting from, like I said, the leftmost area up until this critical point, we can expect to see 0.9251. But we're not interested in the body, we're interested in the tail. So then what we're going to do is the tail would just be the residual. So it'd be 1 minus this, or alternatively 100% minus 92.51% right there. So therefore the resulting tail area would be 7.49. And now we can answer the question. So the question was, what's the probability that the return will be greater than 25%? And we have that answer. The probability that the return will be greater than 25% is 7.49.